Okay, welcome to the second half of Chapter 5. We're going to continue our discussion of polynomials, and today we are specifically going to talk about solving polynomial equations, and we'll be focusing on that for most of the rest of the chapter. Today we're going to focus on solving by factoring, so we're going to be reviewing some of the factoring we've done before, and we're going to see how we can apply factoring to trinomials that are not just quadratic, that have higher degrees. So vocabulary you want to look for today, prime polynomials. We kind of already know what that is. Remember, it's a polynomial that cannot be factored. And quadratic form. So we are needing today a new kind of factoring called the sum and difference of cubes. If you remember in the past, we had difference of squares, which was that x squared minus y squared, for example, factors into x minus y times x plus y. This was the subtraction of two perfect squares. Well, when I have perfect cubes, I actually have a factoring formula for the sum of two perfect cubes and for the difference or the subtraction of two perfect cubes. So you will need to know both of these patterns. They need to go into your factoring toolbox. So if I have two perfect cubes added together, so something cubed plus something cubed, I have to take the cube roots of those so that I can find a and b. And I'll get a plus b times a squared minus a times b plus b squared. When I have the difference of two cubes, it's very similar. It's just a minus b, a squared plus ab plus b squared. So the sum of cubes is plus, minus, and plus. And the difference of cubes is minus, plus, and plus. So you will need to memorize these two patterns. So let's see how we can apply the sum and difference of cubes. Here I have a polynomial x cubed minus 400. Remember, our formula says I would need to have two perfect cubes. Well, we know that x cubed is a perfect cube because the cube root, the cube root of x cubed is just x. So the cube root of x cubed is x. What about the cube root of 400? 400 is not a perfect cube. If we were going to break 400 down and kind of look at its factors, this is what the prime factorization of 400 would look like. And notice there's one perfect cube in there, which is 2 times 2 times 2 times 2. So that's 8. But the rest of the number, which is 2 times 5, or 50, 50 is not a perfect cube. There's not a set of three factors that are all the same. So 400 is not a perfect cube. There's no GCF or anything like this, so this is a prime polynomial. Here's an example of one where we are going to be able to apply the sum of cubes, but after a first step. So remember that we always, when we're factoring, we look for a GCF first. So here we have the GCF of 3x squared, and they factored that out. And look what's left over in here, 8x cubed plus y cubed. Both of these are perfect cubes. 8 is 2 cubed. X cubed is x cubed, so that whole thing is 2x quantity cubed, and y cubed is, of course, a perfect cube. So that means if you're looking back at your formula at the beginning of your notes, in this case, a would be 2x and b would be y, because 2x is the cube root of 8x cubed and y is the cube root of y cubed. So I have to use my formula, the sum of two cubes. Remember that the sum of two cubes is this pattern right up here. So here's my a plus b, 2x plus y. This is a squared, 2x quantity squared, minus a times b plus b squared. So we're following that pattern, and then we just have to simplify. And so here is the simplified sum of cubes, and so my final answer, here was my GCF. And then here was my a plus b times a squared minus ab plus b squared. So we're just simplifying down to the final answer. So that was kind of a longer factoring process than we're used to. That's why you need to memorize those sum and difference of cubes formulas. All right, I want you guys to try this one. Okay, your answer here should be a. And here's the work that goes with that. After you factor out the 2x squared, you're left with 27x cubed plus 64y cubed. The cube root of 27 is 3. The cube root of x cubed is x. The cube root of 64 is 4. And obviously y cubed, its cube root is y. So something you guys need to work on is starting to memorize the perfect cubes. Okay, try this one. All right, in this case, our polynomial is prime. There was no GCF, and neither of these are, well, actually the first one is a perfect cube. Its cube root is 4x cubed. But 27 is a perfect cube, but y to the 5th is not a perfect cube. So in this case, our answer is just, it's prime. We can't factor it. So here is a summary of the factoring techniques we know so far. We know we can try GCF anytime. It doesn't always work, but we should always look for that first. If I have two terms, I usually check for difference of squares, sum of cubes, or difference of cubes. If I have three terms, I look to see if it's a quadratic trinomial. Sometimes it'll be a perfect square trinomial, other times it'll just be general, and we'll have to find the two numbers that multiply to a times c and add up to b. And for more terms, we often try grouping. So let's take a look again at factoring by grouping. This is a review from Chapter 4. Here's our original expression. And I group the first and the last two terms in this case because my first two terms have a GCF and so do my last two. And when I factor out the GCF, remember this factor here has to match. That's now the common factor. So x plus 5 times x squared minus 2 would be the final answer for this problem. All right, here's another one that's factoring by grouping. Here's our original expression. And again, we look and say, okay, is there a GCF with the first two terms? In this case, there is, and with the last two. So we don't have to rearrange our terms in this case. And we factor out the GCF of each section. In this case, it's a. For this part, it's 2y squared. So notice again, a plus 3y matches in both parts. That's now a common factor. And then I pull that out. So I have a plus 3y times a plus 2y squared. Okay, you guys try this one. All right, the answer here should be C. And try this one. The answer here is B. So that kind of factoring we just looked at is factoring by grouping. When I have four terms or more, we try factoring by grouping. All right, let's take a look at this example. We're going to now get into some polynomials that are a little bit longer and more complex. Notice here they're saying we're combining cubes and squares, so we're going to have to kind of combine some of our techniques. So here I have 6 terms, so we automatically think about grouping. So we're going to see how we can group. So in this case, it looks like there would be a GCF in the first 3 and the last 3 terms. The GCF in my first 3 terms is y cubed, so I factor that out. I'm left with x squared minus 3x plus 2. And then in this part of my polynomial, I have a GCF of z cubed, so I factor that out. And notice that both of these parts match, so now that x squared minus 3x plus 2 is a common factor. So I'm left with y cubed plus z cubed times x squared minus 3x plus 2. So we went from here to here, just like with regular grouping, just that this has 3 terms instead of 2. Now, I always have to ask, am I done factoring or not? Well, in this case I'm not, because notice here y cubed is a perfect cube and z cubed is a perfect cube. So this is the sum, the addition of perfect cubes. So this is a plus b times a squared minus a times b plus b squared. In this case, a is y and b is z. And then I notice that here I have a quadratic trinomial. 2 numbers that multiply to positive 2 and add up to negative 3 are negative 2 and negative 1. Since the leading coefficient here is 1, I can just put those numbers directly into my factors. So notice I'm not losing anything as I go through here. Y cubed plus z cubed became this whole piece here. X squared minus 3x plus 2 became this whole piece here, right? So I have to keep writing my factors as I go. I'm just breaking it down as much as I can, and this would be my final answer. All right, let's try this one. 64x to the 6th minus y to the 6th. In this case, this is an interesting one because both of these terms are perfect squares. The square root of 64x to the 6th is 8x cubed, and the square root of y to the 6th is y cubed. But they're also both perfect cubes. The cube root of 64x to the 6th is 4x squared, and the cube root of y to the 6th is y squared. So I can consider this to be the difference of squares or the difference of cubes. Notice what it says here. When you have that problem or you have that option, the difference of two squares should always be done before the difference of two cubes to make your life a little bit easier. So we're going to treat this as the difference of two squares, which means we're not using these, we're using these. So the difference of two squared is just a plus b times a minus b. And then, sorry, let's look at this one more time. Notice that now this is the sum of perfect cubes. The cube root of 8x cubed is 2x. The cube root of y cubed is y. The cube root of 8x cubed is 2x. And the cube root of y is y. So I'm going to use the sum of cubes formula here and the difference of cubes formula here to break it down like this. So these first two factors come from factoring the sum of cubes. And these second two factors come from factoring the difference of two cubes. And that would be, in this case, my final answer. I cannot factor any further. Okay, why don't you guys try this one? Okay, the answer here should be B. And here's the work for that. So I started with grouping. I grouped the first three and the last three terms together, factored out the GCF, and then here was the result of my factoring by grouping. Then I had to factor each factor again. So r cubed plus y cubed was the sum of cubes. That was this part right here. And then w squared plus 6w plus 9 factors into w plus 3 times w minus 3. All right, try this one. Okay, in this case, we end up with A. And here's the work for this one. So first I did difference of squares. That brought me to here. Then I had to factor this first factor again was the difference of perfect cubes. So the cube root of 27p cubed is 3p, and the cube root of k cubed is k. And then I had to factor 27p cubed plus k cubed as the sum of cubes and simplify to get to our last step to get A. All right, let's take a look at this example. It says, determine the dimensions of the cubes below if the length of the smaller cube, so the smaller cube is the white one here, is 1/2 the length of the larger cube. So my larger cube has side lengths of 2x and my smaller cube has just side lengths of x because that's half of 2x. And the volume of the shaded figure, so the volume of the big cube minus the small cube, is 23,625 cubic centimeters. So notice what it says here. When we analyze, like we just said, they named the small cube sides x and the large cube sides 2x because the smaller cube has to be half of the larger cube. And we said that the volume of the object, so the volume of this blue shaded area that you look at back here, or on your notes, the volume of just the shaded area, is the volume of the larger cube minus the volume of the smaller cube. So the volume of the larger cube is 2x because that's one of my edge lengths cubed, minus the volume of the smaller cube is just x cubed, length times width times height, equals the volume, 23,625. So here we simplify. 2x quantity cubed is 8x cubed, and then 8x cubed minus x cubed is 7x cubed. So notice, in this case, I didn't have to do any factoring. Why? Because I only have an x cubed, and I can get the x cubed alone or isolate it by dividing both sides by 7. So I get x cubed equals 3,375. Then all I have to do is move that 3,375 to the left-hand side. So now I have x cubed minus 3,375. And this is where we're going to factor now that it's equal to 0. This is the difference of perfect cubes. You might not recognize 3,375 as a perfect cube, but since you notice that x is a perfect cube, x cubed is a perfect cube, you would want to check and see if 3,375 was a perfect cube using your calculator. In this case, it turns out to be 15 cubed. So our A is like x and B is like 15 in our formula, and we use the difference of cubes formula. Then I use the zero product property. Set each factor equal to 0. X minus 15 equals 0, or x squared plus 15x plus 225 equals 0. When I solve the first one, I get negative 15. When I solve the second one, using the quadratic formula, we're not going to go through that right now, I get a complex number. 15 is the only real solution in this case, and obviously this should be positive 15. So that means the length of the sides of the small cube was 15 and the larger one was